Hi, welcome. So we are discussing about the biasing techniques, and in this we are going to discuss about the voltage divider bias, self bias, or emitter bias. So we can call it as voltage divider bias, self bias, or emitter bias circuit. So here there are the base resistor is split into two resistors, that is R1 and R2. So here there are two resistors R1 and R2 which provides bias to the base of the transistor, and here we have the collector resistor and emitter resistor. So this is the circuit diagram for self bias, and this circuit shows the Thevenin equivalent circuit of the self bias circuit. So the base resistor is as two resistors R1 and R2. Okay. So the V Thevenin plus a base resistor plus collector resistor and emitter resistor. So a simple circuit used to establish a stable operating point is self-biasing configuration. It is also called emitter bias or emitter resistor and potential divider circuit that can be used for low collector resistance. The current in the emitter resistor causes a voltage drop which is in the direction to reverse bias the emitter junction. For the transistor to remain in the active region, the base emitter junction has to be forward biased. So the required base bias is obtained from the potential divider circuit of R1 and R2. Self-bias circuit is used as a constant current circuit. So if IC tends to increase due to increase in IC0 with rise in temperature, then current in RE also increases. Hence voltage drop across RE increases, thereby decreasing the base current. So this decrease in base current will further reduce the collector current, thereby IC is maintained constant. So there will not be increase, the increase in IC is compensated. So this is the Thevenin's equivalent circuit or the potential divider circuit. Vt equal to R2 into Vcc by R1 plus R2, and the base resistance is R1 R2 by R1 plus R2. So writing the expression for the Thevenin voltage IBRB plus VBE plus IB plus IC into RE. So to derive the stability factor, first we have to find DIB by DIC. So DIB by DIC is RE by RE plus RB. Substituting in that equation 1 plus beta by 1 plus beta into RE by RE plus RB. So we are able to derive as 1 plus RB by RE by 1 plus beta plus RB by RE. So the stability factor is very much improved compared to the previous biasing techniques. So S is equal to 1 if the ratio RB by RE is very small compared to 1. So in this case, if RB by RE is very small, then what will happen? 1 plus beta by 1 plus beta. So it is equal to 1. S equal to 1. Okay. So the stability factor is very much improved in the case of self-bias circuit. And similarly, when we derive for S dash, that is dou IC by dou VBE. So when we derive the equation for S dash, so IB equal to IC minus 1 plus beta into IC naught by IB, and we derive the equations and equating to 0. So differentiating with respect to VB and equating to 0. We are deriving at S dash equal to minus beta by RB plus 1 plus beta into RE. And similarly, when we derive for dou IC by dou IC by dou IC naught, dou IC by dou IC naught, that is dou IC by dou beta, dou IC by dou beta, S double dash is derived as IC by beta into 1 plus beta into RE by RE plus RB. So three stability factors we have derived. One is S. First we have derived S. This S is given by DIB by DIC, variation of base current with respect to collector current. Second, we have derived S dash. S dash is DIB by dVBE, that is variation of collector current with respect to VBE. And the third we have derived is S double dash with this DIC by d beta. So that is variation of collector current with respect to the current gain beta. So three stability factors we have derived. Okay, so this is the last. So we have discussed about 5 different biasing configurations for BJT. Okay, starting from fixed bias to self bias, we have discussed 5 different biasing methods. Next we will go for biasing of JFET. So FET, for biasing of FET, FET stands for field effect transistor. So the FET is a device in which the flow of current through the conducting region is controlled by an electric field. So basically BJT is a current control device, whereas FET is a voltage control device. So conducting region is controlled by an electric field, hence the name field effect transistor. Current conduction, here also the current conduction is only by majority carriers. So FET is a unipolar device, while BJT is a bipolar device, FET is a unipolar device. So based on the construction, the FET can be classified into 2 types, that is JFET, junction field effect transistor, and metal oxide semiconductor FET, or insulated gate FET, that is IG FET, or metal oxide silicon transistor, MOST. So these are the different names for metal oxide semiconductor FET, that is MOSFET. And depending upon the majority carriers, JFET has been classified into 2 types, that is N channel JFET or P channel JFET. So where in the N channel JFET, electrons are the majority carriers, and in the P channel JFET, holes are the majority carriers. Okay, so these are the FET and the classification of FET. and these are the drain characteristics. Coming to the drain, there are two different characteristics we can plot for JFET. There is drain characteristics and transfer characteristics. Drain characteristics is somewhat VDS versus ID, that is drain source voltage. So here analogy of transistor and FET, emitter is analogous to source, drain is analogous to collector, and this base is analogous to gate. So when we draw the drain characteristics, VDS versus ID for constant VGS. So this is a drain characteristics, and there are three regions: ohmic region, pinch off region, and the breakdown region. The voltage at which the current tends to remain constant for an increasing of VDS is called the pinch off voltage. So this is called the pinch off voltage, and the maximum pinch off voltage is arrived at for VGS equal to 0. For VGS equal to 0, that current is called the drain saturation current, IDSS. Okay, and these are the various reverse bias gate voltages: VGS equal to -1, VGS equal to -2 volt, and VGS equal to -3 volt. Similarly, when you look at the transfer characteristics, we have drawn for VGS versus ID. So this is how the transfer characteristics will be looking like. Okay, so coming to MOSFET. MOSFET is a common term for the insulated gate field effect transistor. There are two basic forms of MOSFET: enhancement MOSFET and depletion MOSFET. Okay, by applying a transverse electric field across an insulator deposited on the semiconducting material, MOSFET is a common term for the insulated gate field effect transistor. There are two types of MOSFET: enhancement MOSFET and depletion mode MOSFET. By applying a transverse electric field across an insulator deposited on the semiconducting material, the thickness and hence the resistance of a conducting channel of a semiconducting material can be controlled. So this shows the symbol for the enhancement MOSFET, and this shows the symbol for the depletion mode MOSFETs. Then coming to the biasing of the FET, for the biasing of the field effect transistor, for the proper functioning of a linear FET amplifier, it is necessary to maintain the operating point. So as we have discussed in the BJT, for FET also to operate in the stable region, for stable to be stable, we need to fix the operating point. Q stable in the central portion of the pinch off region. So we usually fix the the operating point will be stable in the central portion of the pinch off region. So the Q point should be independent of device parameter variations and ambient temperature changes. So this can be changed by, for the BJT we selected VCEQ and ICQ. Here we have to select the gate to source voltage and drain current, which is referred to as biasing. By suitably selecting the gate to source voltage VGS and the drain current ID, which is referred to biasing. Fixing the Q point. So how will you fix the Q point? Select a convenient value of drain current whose value is generally taken half of the maximum IDSS. So drain current is the maximum drain current, that is IDSS, drain saturation current, IDSS is taken, and half of that value is taken. So that value of drain current is fixed at the Q point. Okay, so the gate to source voltage corresponding to that ID is taken in the transfer characteristics. So look at the transfer characteristics. So here we have drawn the transfer characteristics. So ID is, suppose if ID is 12.5, the half of the value is 12.5 by 2 is somewhat 6.25. So from the 6.25 you plot the IDSS and corresponding VGS is noted. Okay, so that is what we have written here. So plot the assumed value of the drain current and the corresponding gate to source voltage. Draw a line through the plotted point and the origin. So that point is selected as the Q point. Okay. So we can also select. So this method is we can fix this Q point through this method or analytical method. Coming to an analytical method, so the first IDSS is determined, and from the IDSS the value of drain current is determined by ID equal to 1 minus VGS by VGS of the whole square. Okay. So from this we find the drain current. And if we, for example, if we select the gate to source voltage VGS equal to VGS off by 4, then the value of drain current will be ID equal to IDSS into 1 minus, say VGS off is by 4 is 0.25, okay, 0.25 the whole square, which is given by 0.56 times IDSS. So this method is called the analytical method, and also we can draw by graphical method, so which we have previously explained. So we have to plot from the transfer characteristics IDSS by 2, and the VGS corresponding to IDSS may be plotted, and that point may be taken as a Q point. So here we IDSS, so this is ID, so IDSS by 2 and the corresponding VGS may be plotted. So a line is drawn, so that point may be fixed as the Q point. Okay, so this is how the Q point in operating point is fixed in the case of a field effect transistor. and this circuit shows the self bias circuit. So where the gate voltage is where the gate resistance is grounded. So we have VGG equal to 0. VGG equal to 0. VDD is there. Drain power supply is given and VD is there. Okay. When you write the expression voltage equations, VD equal to VDD minus IDRD, and drain to source voltage VDS equal to VD minus VS equal to VDD minus IDRD minus IDRS. So that is equal to VDD minus ID into RD plus RS. And the gate to source voltage VGS equal to VGG minus VS. So here VGG is 0. So 0 minus IDRS equal to minus IDRS. So this voltage drop reduces the gate to source reverse voltage required for FET operation. So the feedback resistance RS prevents any variation in FET drain current. Okay. So this is how the bias stability is achieved. So any increase in drain current is compensated by decrease in drain current. So that is what we are doing. So if at all by any temperature changes the drain current increases, that will be compensated by the decrease in drain current. Okay. So that is what has been explained here. When the drain current increases, the voltage drop across RS increases. Those increased voltage drop increases the reverse gate to source voltage, so which decreases the effective width of the channel. So this reduces the drain current. So any increase in drain current is now compensated. So now the drain current will be decreased. So that is what the thing happens. Next, this is voltage divider bias. So previous one is self bias. Now it is previous one is self bias. Now it is voltage divider bias. So here there are two resistances R1 and R2 to achieve the gate resistance. Okay. So similar to voltage divider bias in the BJT. Okay, and the expression for VGG is R2 by R1 plus R2. So this is voltage divider formula. VGG equal to R2 by R2 plus R1 plus R2 into VDD, and RG equal to R1 R2 by R1 plus R2. Similarly, here also any increase in drain current will be compensated by decrease in drain current. Next one is, this is a fixed bias circuit. So here in the fixed bias circuit, so here we have a drain resistance running to VDD, and we have and the gate is given a separate bias, that is minus VGG, through a gate resistance RG. So here the gate is given a separate bias VGG. So this is called a fixed bias is given for the gate. So this is a fixed bias circuit for an N channel JFET. Okay. So here the FET device needs DC bias for setting the gate to source voltage VGS to give desired drain current. For a JFET, the drain current is limited by the IDSS. So FET has a high input impedance. So one of the characteristics of JFET is that it has very high input impedance. Okay. So this is how the fixed bias circuit is achieved. Okay. So next one is biasing the MOSFET, and also we can have the biasing the MOSFET. So this is the biasing the MOSFET circuit, drain to gate bias circuit for enhancement MOSFET. So biasing that the expression for VGS is R1 by R1 plus RF into VDS. And other techniques, so the voltage divider biasing technique given for JFET can be used for the enhancement MOSFET. So the same technique can which have been employed for the JFET are applicable to the MOSFET. So the voltage divider biasing can be applied, but the self bias technique cannot be applied to MOSFET. Okay. So this is N channel enhancement mode MOSFET, common source circuit with source resistor. So here the expressions for the voltage equations and current equations have been explained, and the biasing of depletion MOSFET. Biasing of depletion mode MOSFET. So this circuit shows the biasing of depletion mode MOSFET. Thank you. So in this unit we have discussed about the different biasing circuits of BJT as well as MOSFET. Thank you.